Welcome to this explainer. I'm going to be taking you through a really detailed macroeconomic simulation today, exploring the potential infrastructural and financial impacts of an impending El Niño cycle. You know, we hear a ton about changing weather patterns, but we rarely get to look under the hood and see exactly how those physical changes map onto an actual economy. Well, that's exactly what I'm going to break down for you step by step using some genuinely fascinating data and models.
So here's our roadmap. We'll start with the climate setup and historical precedents, then dive into the simulation engine itself, the sector-by-sector impact, the broader macroeconomic picture, and finally, how we can proactively prepare. Let's get right into it.
Part 1. The climate setup.
Okay, so let's talk about the baseline driver first, the El Niño Southern Oscillation, or ENSO. When I plug ENSO into our models, I'm effectively setting the stage for a period of notably hotter temperatures, a reduction in baseline rainfall, and considerably drier soils. Honestly, it's kind of like cranking up the difficulty setting on a video game before the level even starts. It's not just a minor shift in a daily forecast, it's a fundamental change in the baseline conditions that our entire agricultural system and infrastructure rely on just to function.
And this is where the sheer complexity of global weather really shows, right? Because ENSO doesn't act in a vacuum. It interacts heavily with something called the Indian Ocean Dipole, or IOD. Now, the IOD is currently neutral, but our models are tracking its transition into a positive phase precisely between August and November of 2026. So the really crucial point here is that this physical overlap happens exactly when our most critical economic activities, like major harvests and peak tourism, are actively happening.
Part 2. Historical weather precedents.
The thing is, I don't really have to guess what happens when these systems get stressed. We can just plot out past events. Think back to the severe 2009 widespread flooding triggered by cyclonic storm Isla, or the 2015 glacial lake outburst flood, often called a GLOF, all the way up to the 2023 Ongar flash floods. These historical markers clearly highlight the infrastructural weaknesses we've faced during previous climate cycles, specifically when it comes to flooding and landslides hitting our critical transport routes.
Part 3. The simulation engine.
Now, I want to be absolutely emphatic here before we go any further. What I am talking about today is a stress test simulation of probabilities. It is not a definitive crystal ball forecast. We're simply looking at mathematical what-ifs to help us prepare. So there is absolutely no need to sound the alarm or panic. This is strictly a tool for intelligent foresight.
To build out this scenario and keep it rigorously objective, I'm using Monte Carlo simulations alongside computable general equilibrium, or CGE, models. If you aren't super familiar with those, basically, these models run thousands of different variable combinations to map out a massive range of possibilities. It lets us establish both the mild and extreme potential bounds for the economy.
So when I analyze the mild scenario simulation, we actually see a fairly moderate, manageable variation from our baseline. The median dips slightly over the coming years, representing just a minor economic contraction. In a scenario like this, the climate systems don't fully synchronize their worst effects, and the economy absorbs the shock pretty well without any severe long-term scarring.
Conversely, if I push the model to an extreme scenario, simulating a peak 3-degree El Niño intensity, combined with a highly active Indian Ocean Dipole, well, the bounds of contraction become significantly sharper. The median takes a much more pronounced dive right around 2027 and stays depressed through the 2030s. But again, remember, this is an extreme simulation to test our ultimate limits. It's not a guarantee of our future.
Part 4. Sector-by-sector impact.
Let's break down the specific sectoral hits based on those baseline parameters. Under a mild scenario in 2026, land transport infrastructure takes about a 5% hit. But under the extreme models, that jumps up to a 10% damage rate. And even more starkly, if you look at electricity sector productivity, mild models show a 3% dip initially, but the extreme scenario projects a massive 28% drop in productivity by 2027. That's a huge gap.
What I find most fascinating here is comparing the different sectors side by side. The tertiary sector, which includes things like tourism, suffers moderately due to autumn and winter travel disruptions from extreme weather. But it's actually the secondary sector that takes the absolute sharpest hit. Why? Because it relies so heavily on hydropower. Warmer post-monsoon conditions accelerate glacier melt, which elevates the risk of those glacial lake outburst floods we talked about, directly threatening our hydropower infrastructure.
The primary sector, basically our agriculture, also faces some direct contractions. The really critical threat window here is from October to December. Remember how I mentioned ENSO causes drier soils and erratic rainfall? Well, that directly threatens water availability right during the crucial rice harvest season. The extreme scenario illustrates a pretty jagged, sustained period of lower overall output.
Part 5. The macroeconomic picture.
So as domestic sectoral outputs decline in the simulation, meaning, we're growing less rice, generating less power, hosting fewer tourists, the model logically simulates an immediate spike in our trade deficit. The extreme scenario spikes quite aggressively in 2026. This happens because our domestic exports fall sharply, and to compensate for that lower internal production, our imports inevitably have to rise.
Naturally, this lower production across the primary, secondary, and tertiary sectors directly translates into lower tax receipts and a drop in royalty income. While the mild scenario remains relatively stable, the extreme scenario maps out a pretty severe, sustained contraction in government revenue, acting as a major drag over the following decade.
Ultimately, the whole shebang culminates in the real GDP variation. While a mild scenario results in a moderate and entirely manageable GDP loss, the extreme simulation shows a sharp initial contraction that doesn't just immediately bounce back. Instead, it acts as a lingering economic headwind, basically due to the structural damage to infrastructure and the lost harvest seasons.
Part 6. Proactive preparation.
Now, bypassing all the dense policy jargon because nobody needs more of that, the absolute most vital takeaway from this entire explainer is the sheer necessity of proactive physical preparation. We just need to focus on the fundamentals. Implementing regular, scheduled maintenance of our existing grids and conducting rigorous physical inspections of all infrastructure before the rainy seasons even begin. We don't need wild reactionary spending, we just need preventative diligence.
I'm going to leave you with this final thought. Knowing that a 10% hit to infrastructure and a 28% drop in electricity productivity are driving the absolute worst of these extreme models, if we actually treat these simulations as a direct guide for early action and rigorous maintenance, how much of that extreme scenario can we simply engineer entirely out of existence? Food for thought.